Hello and welcome to EE233. I'm your instructor, Gregory Myers. In this video, we are going to look at a portion of our physics examples, in this case known as our physics demo. We are going to focus in on the projectile 1D version of 1 through 4. We're going to look at 4 different ways that we can tackle this problem. In the context of by-value and by-reference variables of both a single by-reference variable as well as a vector of values. So to begin with, you'll notice that I have 4 different function signatures here. The first one as simply a void input argument and a void return argument, meaning that it accepts no inputs and no outputs. The function is completely self-contained, including the data collection. In the second example, I'm accepting an initial y as my sole input argument and returning an int, which is going to simply indicate success or failure. In the third version, I am passing a combination of by-value and by-reference variables, with the initial height being the by-value and the t-final, y-final, and vy-final all being by-reference. In other words, they're expected to be updated inside of the function. And then lastly, we are going to pass an initial y, and we want to update the time, y time, and vy time vectors. And these are parallel vectors or parallel arrays, all with the same number of values. And this is determined by the integer n. It says how large are these vectors. So without further ado, I want you to remember to pull up your PowerPoint presentation that accompanies this video. And what we want to do is we want to focus then on our one-dimensional motion. To begin with, we're going to start off with the first version here that collects the info, calculates the 1D motion, and simply displays the results. And all of this is going to be encapsulated into one function here, including the collection. So we're going to start off with the variables that we're going to need. We want to have a double for our y init. We also technically want to have a double for our y final. We're going to have a double for our t init, which is our initial time, and then a double for our t final. This simply provides us with some room to grow this function, to improve this function as we see more uses for it. And then we also want to have a double for our vy init, which represents our initial velocity, and a double for our vy final, which we are going to calculate. Now, we've declared these variables, so we want to go ahead and initialize them. In this case, we're just going to initialize all of these to 0.0. So our y init, our y final, our t init, and then our t final. And then lastly, then our vy init and our vy final. Now, from the equations that I mentioned earlier, we can calculate our t final using the square root of 2 times the height divided by the acceleration. So to begin with, we are going to have t final is going to be equal to the square root, which you can get some help from NetBeans in determining the function signature by just simply typing in the first few letters and then hitting Control spacebar. Remember that this exists in our math.h. So -2 times the y init, and we want then to divide that by our ay, which is a constant that was provided earlier. So ay, you'll see the constant defined above. Continuing on with this, once we have our t final, we can then calculate our vy final. Note also that if we want to expand this out, we could just simply say that t final was going to be equal to the square root of -2 times the y initial divided by ay plus our t init. This assumes that the counter does not start at 0, but even if it does, this provides us a complete formula here. Continuing on with that, then we can, of course, verify our y final. So our y final is just simply going to be equal to our y init plus our vy init times our t final plus then 1/2 a t final squared, or 0.5 times a underscore y times our t final squared. We've got a couple of different ways that we can do this. We can use the POW function and simply square our t final. And then lastly, what we want to do is we want to calculate our vy final, which is essentially the derivative of the position function, and is going to be then our vy init plus our a underscore y times our t final. Now, this is great, but we've not collected any of our initial values from the user. And in this particular example, the one that we're interested in collecting is the initial height. So to do that, what we want to do is we want to prompt the user. So using a printf, provide a friendly message. Please enter the y init, and I personally like to put it on a new line, and then follow this up then with a scanf, and the scanf requires then the data type that was expected. So in this particular case, it's going to be %lf, and the variable then that we would want to store that value in, and specifically the address of that variable. So in this case, it's going to be the address of our y init. Now, on the output side, so this portion handles the input side, but on the output side, then we want to just simply print a nice table here. So using our printf, we want to maybe specify the name of the variable and some distance over then maybe the value. Once again, a new line, and then underneath that, simply have a nice delimiter for the table. Doesn't really matter how you do this. This is mainly just aesthetics, so you can always improve on this, refine this, but we're going to put a bar then at the beginning and the end of our table. And then inside our table, we want to print out not only the final values that we calculated, but then also the initial values. And so our y init is going to be a %. We're going to go ahead and do this to 4 decimal places. And I'll tell you what, let's do something a little bit different here. Let's actually specify then the total number of places. So we're going to do %8.4f. And in this, we are going to simply, in that placeholder, we're going to put the y init. Likewise, we might as well go ahead and print out the y final to see if it deviates significantly from what we expect it to. We're going to follow the same pattern here of the percent 8.4f and our y final, and continue this on then with our t final. So if you want to, you can be a little, I guess you could say a little lazy here. We're going to simply copy and do a little copy and pasting here. So there's our t init and our t final. A note for this example, once again, our t init is assumed to be 0. We haven't changed it any. We haven't prompted the user, for instance. But once again, for further use, then we're going to provide it as a placeholder. And then also we want to have the vy init, which once again, we have not prompted the user. We're simply displaying the values here. We haven't prompted them for an alternate value, so vy init should be 0, and our vy final, which was calculated. All right, so provided we've got no mistakes on this one, let's go ahead and build it. Cross your fingers. It'd be nice to have a few errors occasionally. What do we have here? Yes, so an implicit declaration of the built-in function. I kind of knew this one was going to be coming because, as I mentioned earlier, we have to include the math library, and I did not when we set this up. So it's a nice gentle reminder here. So that we want to include, rather, not define, we want to include our math.h. That should get rid of that particular warning. And let's go ahead and build it one more time. All right. Go ahead and open up a new command window. We want to cd to the location where you were working on this project. In this case, it's my documents, courses, EE233, projects, and this one's called my physics demo. I'm going to go into the distribution folder, into the debug, into MinGW, and I should have a physics demo.exe. And right now it's going to do absolutely nothing. And why is it going to do absolutely nothing? Because I have technically not called our projectile 1D version 1 function. And we simply come down here and we add this projectile 1D version 1, and there is no return value, and we're not passing any input arguments. So at this point, then that's all we need to do. Come back over here to our command window, and we're prompted to enter in a y init, which I'm going to put in as 100. And you'll notice that I've got this table now printed out horizontally. We can see here that we did not include any new lines, only up here at the top. So we need to come back in here and refine this just a little bit. Once again, I'm doing some of these errors intentionally here so we can sort of see in situ that nothing works perfectly the first time. And we go ahead and build it. And now let's see what we have here. So we have 100, and we have a nice table. Lines up pretty nicely with our y init of 100. Our y final is minus 0.00. That just means that basically it's really close to 0. We've got some error out further. We could increase the number of decimal places that we are presenting, but effectively what we got is 0. Our T final was 2.4922 seconds. Our VY init was 0, and our VY final was a minus 80.25. So let's now take a look at the version 2 of this problem, which calculates the one-dimensional motion and displays the results, but it accepts an input argument of y init. Now, technically, we could have written this function to accept multiple input arguments, say a y init, a y final, a vy init, and a v final, for instance. And basically what would happen is it would expect different arguments would result in different equations. The simplest version of this is just simply the y init, accepting a single input argument. So what we want to do is we want to see how this changes what we do inside this function. So in this case, we're only calculating and displaying, but not actually collecting the info. That's left to be done somewhere else. So what we're going to do is we're going to borrow a little bit of our code here. Particularly what we can do is we can borrow not only our equations, but also our table here. So the significant difference is we do not need to declare a y init. Instead, that is handled through the input argument of the function. So we're just going to go ahead and copy all of the variables down except for the y init. We are going to then turn around and initialize all of the variables except for the y init. In other words, you don't want to initialize a variable that is being passed as an argument to your function, because what you're going to do is essentially overwrite the value that was intended to be passed. But we do want to initialize all of our remaining variables. And from there, then we want to skip over printing the prompt to the user in the scanf that captures our y init and just focus on the equations and the printing out of the values. And so down here, then we can just copy and paste our code over. And you can see there's not a whole lot of changes between the two. But in this case, we don't have our y init yet. We're passing it as a variable to this function. There's an input argument to this function. We aren't collecting it inside, which means that leaves us to do this up in our main. And we've got a couple of different ways that we can do this. So this function, I'm going to put a little note up here, assumes we collect the y init inside the function. And our version 2 assumes that we collect the y init outside the function. And so we can do this a couple of different ways. First, we can just simply say projectile underscore 1D version 2, and then put in our value, hard code the value. That's perfectly fine. It accomplishes the exact same thing. As a matter of fact, I'm going to uncomment my version 1 and go ahead and build this. And I come over here, I'm going to clear my command window using CLS and rerun it. And you'll notice that I was not prompted by the user. It simply passed the 100 to the function and went ahead and calculated the results and displayed them in a table, exact same values that we saw earlier. So this is one option. So this is the hard-coded option. The second option is that we go ahead and declare a variable outside in our main. In this case, it's going to be a double, and we're going to declare y init. And like we did in the earlier example, we have a printf where it says, please enter y init. And I tell you what, I'm going to real quickly check, please enter the y init. I wanted to see, keep consistent here. Followed by a new line and then scanf accepting a %lf as our input argument and then storing it at the address of our y init. And then at this point, what we can do is we can say projectile 1D version 2, and we pass to it our y init variable. So this allows for the user to enter in the value at runtime. So this passes the value entered at runtime by the user. So kind of the same results that we saw earlier, except we've pushed where we are prompting the user for the input argument now to outside the function. So same thing, I'm going to put in 100.0, same results. So you've now seen 3 different ways to go about doing this. And as a fourth one, what we're going to do now is we're going to leverage our argc and argv. And I'm going to go ahead and comment out real quick our second iteration here. And instead, what we're going to do is we're going to leverage the argc and argv. Now, this means that I'm going to pass a value from the command line. And to do so here, just a quick reminder, we want to print our argc and our argv just so that we can tell how many of each we have. So, or what are, or I guess you could say how many arguments they are, we have, and then how many of them, excuse me, how many arguments we have and what they are. So we're going to start off the argc, then we simply want to print out using %d the count. And then what we're going to do is we're going to build using a temporary variable here, int index, which we will need in just a little bit anyway. We're going to build a for loop. So for index equals 0, index less than argc, index plus plus. What I want to do now is I simply want to print out each one of the command line arguments. So this is going to be a %. Tell you what, we will do it this way. We'll say argv square brackets %d, and then the value, which is going to be a %s, followed by a new line. And so the first argument is going to simply be the index, and the second one is argv square brackets index. Now, we're actually going to move this to the top here because we're going to find this function pretty useful, or this little loop pretty useful. We'll build it one more time, and we're just going to use this as a gentle reminder of how our arguments work. So if you come along here and run this one more time with no arguments, you'll see that the arg count is 1, and that only argument is the name of the executable. However, if I come along and do physics_demo.exe, and then I follow it up with my 100.0, you'll see that I in fact get 2 arguments, with the second argument being the 100.0. So how am I going to leverage this? Well, if we know how many arguments are passed, then we can decide to call our function if enough arguments are passed. So in this particular case, since we know that it's going to take at least 2 arguments, the executable name and then an integer value, to have enough arguments to be able to successfully call our projectile 1D version 2, what we're going to do is we're going to build a crude if structure. And it's going to simply check to see if argc is equal to 2. We assume the user wanted to call the projectile 1D version 2. Okay. And what we do there is we use our y_init variable one more time, and we use a function. It's actually a family of functions here. We use our A to F function that will take a string from, in this case, the command line and convert it into the equivalent double if it can. So in other words, it's going to take the 100 that we want to pass from the command line and convert it into a double from a string. And to do that, we simply specify our argv square brackets 1. Now, your first instinct is going to be to say argv square brackets 2, but remember that C is 0-based indexing. And at this point, then what we can do is we can simply call our projectile 1D version 2. And just like the earlier example, now we can pass the y_init, and this gets it from the command line. So it passes the value entered at runtime from the command line. So no prompting the user, no printfs, no scanfs. And let's see how this one works. So build it. Come over here to the command line and clear the screen one more time. And now what it's going to do is it's going to take the 100, it's going to pass it to our function, and we once again get the table that we expected. If I forget to pass the 100, then it does nothing, because right now it's currently checking to see if argc is equal to 2. In a more advanced video, we're going to come back and we're going to tweak this so that you can actually call different versions of these functions based on additional switches. But right now we're just going based on the arg count of 2. All right, continuing on with this, now we want to take a look at the third version of this function. This time around, we're going to pass to it a single value ByVal, excuse me, and then the other values are going to be passed by reference, the other variables rather. Let me rephrase that. We're going to pass one variable by value, and the other ones we're going to pass by reference, which means that they can be modified inside the function. And we're not returning them, we're actually modifying the actual value at that location in memory. And once again, we can actually be sneaky here and borrow some of our code. And the first instinct would be to put all of this over here in this version. But notice that I said that this function is going to do no display, nothing at all. Instead, what we want to do is we want to let the main display the output. All right, and to do that, then we don't need as many of our variables or the initialization that we had earlier. So in other words, we can be just a little bit more selective in that the only thing that we actually need here is going to be our t-final. Actually, we're going to be past our t-final. The only thing that we do need as far as our variables is actually going to be our t_init. And this is once again just for future expansion. Technically, we would want to include this as an input argument. And our vy init. And initialize t init to 0, or vy init equal to 0. And now what we can do is we can come up here, we can borrow the same equations that we had last time. And we can paste them here, but with one slight difference here. So what we want to do is we want to actually change the values at these locations. Okay, so everywhere that we pass one of our variables by reference, we need to dereference them inside of our function. So in this case, our T final is editable because we're passing it by address. Our Y final is editable because we are passing it by reference, and our VY final is editable because we're passing it by reference or by address. So everywhere that you see a T final, we need to change that to a dereference of our T final. And let's make sure that we've got all of them. The VY init and the Y init are both, our VY init's actually a local variable that we're initializing 0, or Y init is just passed by value. So I think we've got all of them here. All right, so in this case, then go ahead and build it. All right, now we have to think about how are we going to call this particular function. Well, if you come back up here now, what we want to do, we can go ahead and move this up to the top of our main, because if anything, we're going to probably leverage this in the future. But what we want to do is, as long as we are provided with enough information, in this case, as long as we have those 2 arguments, we're just going to test this one from the command line. What we can do is we can capture the Y init from the command line, and instead of calling the projectile 1D version 2, we can call the projectile version 1D version 3. But the difference is going to be that we not only need to pass it a Y init, but we also need to pass it by reference our T final. So in other words, an address to a variable called T final, the address to the Y final, and then an address to VY final. Now, the variable names themselves don't have to match the function signature. However, though, we do not have these variables yet, and so what we need to do now is come up here and declare them. So we have a double of T final, a double for Y final, and lastly then a double for our VY final. Let's go ahead and build it one more time. And so far, so good, except for the fact that we're not actually printing anything out, because if you recall, our projectile 1D version 3 did not have that responsibility. We put it here at the description in the function. If you'll notice, no display. So what we want to do instead is we want to capture our table here. So we'll copy this table. And in this case, we're going to put it out in our main so we can see how it works. We're actually going to put it under this particular branch here of our if statement. And in addition, we need these temporary variables of our T init and our y init, or what we can do is we can simply just hard code these values, because for this specific example, we are not providing those. But notice that we are providing the y init by virtue of the command line. And then we are calculating the y final, the t final, and the vy final. So now if we build this, if we don't have any errors, we come over here to the command window, type in CLS, and then run our demo one more time. You'll see that you get yet again the exact same table, now done a different way. Okay, so now the obligation or the responsibility for printing out the table falls to our main, not to the function itself. Which brings us then to the last iteration. In the last iteration of our projectile 1D version 4 now accepts the same single input argument ByVal, the y init that we're going to get from the user. But this time around, then the assumption is that the user is going to provide a variable, a ByReference variable of an array of time, y time, and vy time, and is going to specify how many data points they wish to calculate the time, the y time, and the vy time at. All right. Once again, there is no display inside of here, so the responsibility for displaying this is going to be pushed outside to an additional table. So let's go ahead and get started with this one. Just like before, we have a double of our y final, a double of our t final, a double of our t init, which we are going to assume to be 0. We're going to calculate the t final, but also what we want to do is we want to include in here a double of our vy init. And then our time, our y time, and our vy time are all references to vectors of values. And the last variable that we need is going to be an index variable that is going to allow for us to loop through those values. So we're going to create an index here. We're going to go ahead and initialize some of these. So our y final is going to be equal to 0. We actually are going to go ahead and calculate it. Our t init is going to be equal to 0. Once again, this is just for further refinement in the future. T final is going to be equal to 0.0. And then our vy init, once again, much like I said earlier, is just a placeholder for future work. We're being passed our y init. So the first thing that we can do is we can use that to calculate our t final as simply the square root of the -2 times the y init divided by our a y. And then, as I mentioned earlier, we could add our t init to that. Now, where this gets different is we want to look at the number of data points that the user has requested, or the number of elements in the vector. And what we want to do then is we want to use that number to discretize, or to break up the time from t initial to t final into equally spaced time segments. And so to do that, what we actually need is we're going to need one more variable in addition to our t init. This is a convenience variable, and we're going to call this one t delta. And the whole purpose of t delta then is to be able to calculate the difference in the time steps. So our t delta is going to simply be equal to our t final minus our t init. And it is going to be then the size of the T delta is going to be essentially related to the number of segments that the user wants, and the number of segments is going to be related to the number of data points by simply n minus 1. All right. And once again, I like to use an abundance of parentheses here. So what we've calculated now is the time difference between data points. All right. Now, from here, we simply build a for loop. We start off for index equals to 0, index less than n, where n is the number of elements in our parallel arrays or parallel vectors, index plus plus. And the idea here is that we are simply going to loop through, and for each value in the time vector, we're going to calculate the y time and the vy time. So the first step is going to be to take this time vector, and so time square brackets index, which is going to start off at 0. So the first time is going to simply be equal to our t init plus index times our t delta. So the first index is going to be 0. So 0 times t delta means that this is just going to be the value of t init for whatever it happens to be. In this case, it's 0. We can then use this approach to calculate our vy as a function of time. So vy underscore y underscore time index is going to be equal to our vy init plus our a underscore y times then the value at that location in the time vector. So time square brackets index. And I accidentally jumped over the position here. My apologies. So y underscore time square brackets index is going to be equal to the y init plus our v underscore y init times whatever the value is at that particular index in our time vector. Notice in this particular case that vy init is 0, once again allowing us just for some future expansion. And then lastly then plus the third term, which is going to be in 1/2 at squared, or 0.5 times our a underscore y times the POW function utilizing the time square brackets index and 2. Okay, so that's you can multiply the time index times the time index twice, or you can use the POW function. I want to check, yes, I did want to make sure that I used a double here. Technically, it's perfectly fine if you use an integer, but just to be clear, the POW function actually accepts as its function signature a double. All right, as in our last example, there is no printing being done inside this version of the function. So we want to go and build this project just to make sure that we don't have any issues with the 1D version 4. T underscore final. Simply missing an equal sign there. That's forgivable there. So let's see, build it. All right, and then let's come back up here to our main, and let's figure out now how we're going to do this, because this is going to be a little bit different than the last time around. And so last time around with our version 3, we expected singular values. So a t final, a y final, and a vy final. Those were all singular values. They were passed by reference, but they were all singular values. And so what I want to do now is I want to create another group of variables here. As a matter of fact, I'm going to isolate these just a little bit. And these are going to be our vectors. Okay, and the first thing I want to do is I want to go ahead and specify the size for n. Okay, so you could accept this as a input argument if you would like to. You can dynamically generate it, but essentially what I'm going to do is I'm going to specify my n being a fixed size, in which case then what I'm going to do for this example is I'm going to simply say double of our y as a function of time is just going to be 11. Okay, so there's 11 elements in this. Our t, our time vector, is also going to have 11 elements in it. And then our vy time is going to likewise have 11 elements in it. So we're just going to keep track of our n manually, essentially. Okay, so n is going to be equal to 11. So I'm just going to leave this one commented out. Well, we can come back and revisit how you would do this to do this a little more dynamically. Long story short, if you come down here, tell you what, I'm going to backtrack just a little bit here. I am actually going to use n. We won't dynamically set it yet. So in this case, I'm just going to initialize n equal to 11 because I would like to use it down here. All right, so what we want to do now is we want to print out the table for our y init and our y final, but we won't have these values anymore. We aren't going to have these variables because instead this time around what we're going to do is we're going to call the projectile version 4. And the projectile version 4, 1D version 4, is going to accept the y init. It is going to accept a time vector, and we don't need the ampersand in front of it because it is a vector. It's going to accept a y time, a vy time, and then lastly our n. We would, however, still like to have a nice table like this. So I'm going to copy this table. I'm going to leave this one alone for the purposes of the previous example, but I am going to copy it because we're going to utilize it with some slight changes so that you can see that you can actually print out then specific values in the vectors as well as the vector itself. So in other words, instead of printing out the y underscore final variable, what I'd like to do is I simply want to specify the y underscore time and the n-1 index. In other words, if there's 11 elements in the vector, we want to print out the 10th element. Likewise with our t final, instead of that, we're going to have our t vector. So this is going to be time square brackets n-1, and then our v underscore y final is essentially going to be v underscore y underscore time square brackets n-1. So this allows for us to have that nice table. In addition to that, I want to see all of the values in the vector. And to do that, I'm going to sort of separate this value out and these sets of values out. And so I'm going to use a for loop for this. And so for index equals 0, index less than n, index plus plus. In other words, I'm going to loop through each one of the vectors, and I simply want to then print out a nice table at the corresponding index. All right, and then to do that, let's tell you what. Let's do a little more refinement here. I'm going to print f. Maybe go ahead and put in a new line here, and then for this table here, we're going to have print f, the index, and then the value. And specifically what I'd like to have here is maybe instead of the value, how about if we do it this way? We'll say the index and then the position or the y as a function of time, the time itself, and then the vy time. And then once again, our nice little line here to separate the portions of the table. Inside of this, we're simply going to use a printf, and we're going to specify the first one as a %d because that's an index, which is the integer. Once again, I'm going to attempt to estimate here my spacing. So this is then going to be %8.4f, tabbed over a little bit further, %8.4f, and then %8.4f followed by a new line. For the first value is just simply going to be the index. Second one is going to be the time, but the specific value at a specific location, in other words, a specific time in my time vector, and then y underscore time square brackets index, which will be the third placeholder, and then lastly, v underscore y underscore time square brackets index. And then let's go ahead and build this real quick. And let's see if we've got any mistakes, perhaps maybe a spacing issue. Let's run this one more time. And you'll see now that you've got two tables, one going to be the essentially the beginning and end values, or y init 100 and minus 0, or very, very close to 0, a t init, t final, and vy init and vy final, and you can see how it changes as a function of time. So we have 11 data points in our table. And that about wraps it up for the 1D example. I'm going to go ahead and stop the video here. As always, if you've got any questions, comments, or suggestions, don't hesitate to reach out to me. I felt that it was useful for us to see all 4 of these examples together. The goal of this is for you to see how the behavior shifts. In other words, for instance, where you are prompting the user and then printing out the data based on the function signature. And then the last part, particularly the version 4, then demonstrates how you would get, how you would utilize vectors to be able to update multiple values. So in version 3, you update a single value, and in version 4, you update multiple values. Once again, if you've got any questions, don't hesitate to reach out to me. Thank you very much.